Assalamualaikum warahmatullahi wabarakatuh, and good day. Hi everybody. This time we will continue our class of thermodynamics. The topics that I will cover today is about steam power plant. There are two objectives that you have to know in this topic, in this day. That means, number one, what should you know is you must know how to analysis and do the calculations based on the ideal simple Rankine cycle. And number two, you should also know how to calculate and do the analysis based on the actual Rankine cycle. Okay, let's go about steam power plant. Steam power plant, also known as a thermal power station. It is a power plant in which the prime mover is steam driven. Actually, this steam power plant is based on the water. That is, water is heated, turned into steam, and spin a steam turbine which drive an electrical generator. A thermal power station is a power plant in which heat energy is converted to electrical power. As you see in this slide, this is a concept of how the steam power plant work. Okay, based on the water, we put in the boiler, and we heated the water, and the steam from the boiler will go to the turbine and turn the turbine, and from there the turbine will rotate based on how much energy from the steam is produced, and then connected to the shaft to the electrical generator, and this generator will produce or will give us electricity. Okay, before we go for the steam power plant, let's go previously know what is the Carnot cycle. Actually, this Carnot cycle I have covered in last lecture. What I have told you that in the Carnot cycle there are 4 devices that operate as a basic in the Carnot cycle. The devices such as pump or compressor. Number 2 is boiler. Number 3 is turbine, and number 4 is condenser. This is a TS diagram for the Carnot cycle. As you see in this diagram, based with the schematic diagram at the left, number 1 and 2 actually is isentropic compressor in compressor or pump. Okay, the number process here is an error. That means this is number 1 and number 1 to 2. Okay, number 1 to number 2, isentropic compression in the compressor. 2 to 3. Okay, let me correct this. Control 2. Okay. This one. 1 isothermal heat addition in a boiler. 3 to 4, okay, this one 3 to 4, okay, isentropic expansion in turbine, and this is 4 to 1. That's made isentropic heat rejection in condenser. Okay, from these kind of cycles, we can get the thermal efficiency based on the equations, the simple equations, W net over Q in. That means we can simplify this equation to 1 minus Q out over Q in, or 1 minus TL over TH. TL over TH based on this diagram. TL is heat source temperature, H is heat source temperature, TL is heat sink temperature. Okay. The Carnot cycle is the most efficient cycle between two specified temperature limits, but it is not a suitable model for power cycles. Okay, we can use Carnot cycle as a most efficient cycle operating, but it is not suitable for power cycle. Why? Because in process 1-2, okay, you look here in process 1-2, limiting of heat transfer processes to two process system severely limits the maximum temperature that can be used in the cycle. And number 2, the limitation is the turbine cannot handle steam with a high moisture content because of the impingement of liquid droplets of the turbine blades causing erosion and wear. Okay, that's mean process 2 and 3. Next is, it is not practical to design the compressor or the pump that handle two processes. If you look in process 4.1, okay, 4.1 here, number 4 and 1 is a compressor or pump. That means it operates in the mixture region, so it is not practical to design. In TS diagram in B, it is not suitable since it is required isentropic compressions to extremely high pressure and isothermal heat transfer at various pressures. Okay, this is not suitable to do the design like this. Okay, because it's much more high pressure and isotropic heat transfer at various temperature. Okay, next we go on. For Rankine cycle, use the ideal cycle for power vapor power cycles. This is a schematic diagram for Rankine cycle. It actually have 4 devices. Number 1 is a pump. Number 2 is boiler. Number 3 is turbine, and number 4 is condenser. Because it is use water, so we use this boiler as a device for heating. Okay, based on this here, for process number 1-2, the water will go when pump is turned on, the water will go in the pump, and then isentropic compression in the pump. 2-3, constant pressure heat addition in the boiler. 2-3, and at this heat addition is at 3-4, isentropic expansion in the turbine. Expansion will be occurred in this turbine, and 4-1 is constant pressure heat rejection in the condenser. The TS diagram is as shown as the diagram. So here is a number 1, process number 1 is isentropic compression. 3-4 process here is expansion for turbine. Heat addition is 3-2, and 4-1 is heat out or heat rejection. Okay, the analysis of the ideal Rankine cycle based on the process number 1 2, where it is occurred in the isentropic compression and pulp. Actually, pulp is a open system. So from the open system equation, that means SFEE specific SFEE based on the equation. So we neglect potentials, kinetic energy. So roughly it will come, the equation will become is like this, where when we want to find the work dot pulp is equal to m dot delta h. So delta h can be converted to definition of enthalpy. So it will become NV delta P. So from here we know the P2 and P1, so we can find work or power for the pulp. For process 2-3 is constant pressure heat addition in the boiler, okay, at the boiler. So using the SFEE energy equations, only heat have in this equation. So heat is equals heat plus m dot 2 h2 is equals to m dot 3 h3. So simplify the equation. So you have this equation. You can find Q in the boiler. Q in is equals to Q boiler. So from Q boiler we know that the efficiency of boiler times m dot fuel times calorific value of the water. So we can also have Q dot boiler. So m dot f is mass flow rate, CHV is calorific value of fuel. For process 3-4, that's the expansion in the turbine. So turbine we also assume it as an isentropic process. So from here, using SFEE energy equations, so you will get power out is equals to m dot delta h. That means you have to find h3 and h4. For process next is process 4-1, heat reaction in the condenser. Also using the specific SFEE equations, so you will get the equations. Finally, Q dot out is equal to m dot delta h. So like boiler, Q dot condenser is also can be found from m dot Cw times CCW plus time delta T. So based on these all equations, when you want to find the thermal efficiency, so you have to find also W net over Q in. So W net come from delta H at process 3-4 minus delta H at process 2-1 over Q in is delta H3 minus H2. So from this equation you can get thermal efficiency. Okay, this is a simple problem for ideal Rankine cycle. So consider a steam power plant operating in a simple ideal Rankine cycle. Steam, that means enter the turbine at 3 megapascal. There was steam here, enter the turbine, and 350 Celsius, and is condensed in the condenser here at a pressure of 75 kilopascal. So from here, determine the thermal efficiency of the cycle. This is a schematic diagram that has been given, and you have to draw TS diagram to make it more simple, and you can understand how this process works before you do the calculation. Okay, this process for the process. Okay, after you have drawn TS diagram to familiar or to make it more simple for you to understand. Okay, and then you have to calculate or find each step number 1 to step number 4. Okay, for step number 1, you know that P1 is 75 kilopascal. At this state H1 is equal to HF. That's mean 384.44 kilojoule per kg, because at state 1 it is the point is on the saturated liquid line. So V1 is Vf is equal to Vf at 75 kilopascal, and T1 is equal to desaturated at 75 kilopascal. So we go to state number 2. State number 2 is equal to 3 megapascal given, and you also know that S2 is equal to S1, and using the work pump equations where it is equal to V1 delta P, so V1 is 0.001037. That means this value you can get in the properties table at pressure 3 megapascal. P2 is given, T1 also has been given, so you got work pump. So when you have this value of work pump, you also know that work pump is equals to H2 minus H1. So from here, H2 will get 387.47. Step number 3, that means at the exit of the turbine, P3 has been given, T3 also has been given. From here, you will look these two properties, using these two properties, and look in the properties table, and from there you will get H3 is equal to 3116.1 kilojoule, and also at that positions of position in properties table at P3 and T3, you also get S3 is equal to 6.745 kilojoule per kilogram Kelvin. This is where, but you also have to remember P3 and T3 is in the superheated or the mixture. But in this diagram, P3 is the superheated. So at step number 3, just go straight to the table of superheated. Step number 4. At step number 4, where at step number 4 here, you must find first whether step number 4 is in the mixture region or in the superheated region. So to do this determination, so from P4 you know that S3 is equal to S4. So using S4, make the comparison with SFG at pressure 75 kilopascal. So from there you know that state number 4, that means is in the mixture region. So when it is in the mixture region, so you have to find the value of quality S, because this value of quality will be using in the equations to find H4. H4 is equal to HF plus H4 times Hg minus Hf at pressure 75 kilopascal. So put all the values that you have into these equations, then you will get H4. To find Qin, using the knowledge that you know, Qin is H3 minus H2, So just put in the value, then you will get Q in and also Q out using the equations. Put the value, then you will get Q out. From there, the thermal efficiency of ideal simple Rankine cycle is based on the formula W net over Q in, or simplify that equation, thermal efficiency, then 1 minus Q out over Q in, and then the value will, all the values that put in the equations will give the last answers of 26% of thermal efficiency. Okay, this is an example. Okay, it's an example on how you can determine the thermal efficiency based on the simple Rankine cycle. Uh, 26. Okay, this is also how to calculate. Okay, this is also how to calculate the thermal efficiency, but this is based on the basic Q net over Q in. Okay, what I told you right now. I just write in last slide. Okay, now we look on the deviations of actual vapor power cycle from idealized one. So when you deal with this case or these cases where in the actual situations where the compressor and the turbine have the efficiency, we call it as the isentropic efficiency of compressor, pump or turbine. So when you know that these efficiencies, so you have to find the actual value for point number 4 or at state number 4. That's mean for the actual value. Okay, look at this DS diagram. Okay, that means when you want to do the calculation, you have to find 2A if you base on the compressor, and also 4A is you calculate based on the turbine. So to know this value of 2A and 4A, this is the equations that you have learned before this. That's been in last chapter. That's when isentropic efficiency. The equation is like in here. For pump here, that means work ideal over work actual. For thermal isentropic thermal efficiency for turbine, work actual over work ideal. So put all the delta H here, and then you will get the answer for 2A and 4A. Okay, this is show how this concept been determined. This for the ideal cycle, that means all the graph is in the straight line. Okay, but for the actual process of Rankine cycles, when that means what it means by actual, when you do the experiment, that means the graph will become not like the ideal one. This is what we learn is on the class is on the ideal or theoretical graph, but based on the experiment, the graph will be like a dot line. So this is what we call the actual cycle or Rankine cycle. Okay. Okay, let's look on how we calculate based on the actual vapor power cycle. Okay, problem 6.6. Consider a steam power plant that operates on a simple Rankine cycle and has a net power output of 45 megawatt. Steam enters the turbine at 7 megapascal and 500 Celsius and is cooled in the condenser at a pressure of 10 kilopascal. By running the cooling water from the lake through the tubes of the condenser at the rate of 2000 kg per second. The isentropic efficiency for the both turbine and compressor are 87%. Show the cycle on the S diagram with respect to saturated lines and determine A. the thermal efficiency of the cycle, the mass flow rate of the steam, and also the temperature rise of the cooling water. These are all the answers. Okay, this TS diagram has been shown to you, but in this case, it wants you to show on the TS diagram. So firstly, you have to draw this TS diagram. The TS diagram that you will draw is will show like this. Okay, where it said in this question it has the isentropic efficiency of turbine compressor. So you have to draw the dot line and also the straight line. Okay, for both pump and turbine. Okay, this is schematic diagram what happened. So we go for state number 1. P1 has been given, X1 0, so it's saturated liquid. H1 is equal to HF. V1 also is equal to VF. Find it in the properties table. Okay, step number 2, P2 is 700 kilopascal. H2S, that means for ideal, is H2 delta P plus H1. This is the work pump formula. So using this equation, you will get the H2S value. Okay, from there, using the isentropic efficiency for pump equations, simplify that equations, then you will get the actual value for H2A. That's mean 199.86 kJ per kilogram. For step number 3, that's mean for turbine, we know that is superheated. So just straight away to the table of superheated in property table, get H3 based on the pressure value and also temperature value. You will get H3 and S3. For step number 4, P4 is 10 kilopascal. This is given to you, but you know that S4 is equal to S3. So using this comparison, that means you have to compare S4 with SFG. Sorry, F4 with FG at pressure 10 kilopascal. From there, you will find that the S4 is bigger than FG at 10 kilopascal, so it is superheated. So using the superheated table, in properties table, H4S will be, you will get the answer on that. And again, using the isentropic efficiency of the turbine formula, simplify that formula, then you get H4A. Okay, and the thermal efficiency is basically based on 1 minus Q out per Q in. So 1 minus Q out is H4 minus H1, Q in is H3 minus H2. Sorry. Take all the values, put in the equations, then you will get the thermal efficiency is 33.8%. Okay, this must be based on the actual value. Mass flow rate is based on W net dot is equal to M delta H. So put the value that you get on the calculation, and then you will get M dot is 41.42 kilogram. And for C, delta P. Okay, for Q out, that means M delta H minus H1 is equals to M dot W Cp delta T. So you want to find delta T, simplify, arrange again this equation, then you get 10.52. Okay, I think that's all for today. Thank you very much for listening.